Hello everyone, how are you doing? Hope you are well. Today we have another tutorial using the Arduino board, and we're about to measure alternating current using the sensor ACS712. I'm using the 30 amp version. You can use 5 amp, 10 or 20, it depends on your application. So this sensor uses the Hall effect, which means any current passing through it will create a voltage proportional to that current, and we're gonna measure that voltage using the Arduino board. So this module works with both DC and AC signals, but here we're about AC only because it's very tricky and it can cause some problems. But thanks to our library, which is filters library, we're gonna measure any current, any shape, not only the sine wave. So the last time I used that library with the module ZMPT101B to measure voltage up to 250 volt. You can see the tutorial in the link below. It was very simple and easy, and we created a voltmeter like that can measure any true RMS, and we showed too that it's better than some cheap multimeters. So just before you purchase that module, make sure to use the correct one, because I tried to play it safe and bought the 30 amp version. It was 2 years ago, but unfortunately 30 amps is very big, so in small amps it will give a lot of fluctuation. So choose 5 amps or 10 amps. Don't play it safe because you will lose precision. So in this video, first we're gonna just use the module with the Arduino to see the shape of the AC signal. Then we're gonna see a simple code on how to measure sine wave signal, and then in the last we're gonna show another code to measure any signal, like with any shape. And in the last we're gonna add our OLED screen to show the current value. So just like the last time, I'm gonna do the test on an incandescent light bulb using a light dimmer to change the current value. Okay, let me explain this mess. First, I have a power outlet, a wireless power outlet. I control it by this remote control. Then it's wired directly to this light dimmer. I fixed it with some tape. I have a direct wire from the power outlet to this light bulb. It's a simple incandescent light bulb. Then the other one goes to multimeter to measure the amps. Then from the multimeter it goes to the ACS712. Then from the ACS712 it goes back to the light bulb. So first let's do a small test. Okay, the light dimmer works well. Now let's test our multimeter. Okay, AC. So the light dimmer is on full cycle, and as you can see it's about 0.3132 amps, and that's right because I'm using 75 watt incandescent bulb, and here we have about 220 or 230 volt AC, 50 Hertz. It works well. Let's dim it. Sorry. It will go back to there around 0.22 amps, 21. So those light dimmers are based on a triac, so you know that weird format you have or weird shape of the signal. We saw that when using the voltage sensor. Now let's test with our Arduino. So the module is very easy to wire. It has 3 pins, VCC, ground and signal. VCC works with 5 volt, and the signal, it has a analog output. So as you can see, my Arduino is now powered, and the module has that red light. It means it's working, and this is the code I'm using. It's very simple. I'm declaring the pin for the sensor, it's A0. Then I'm declared this I as for the current value. Then I define the pin mode, it's an input. I read that raw data from the sensor and display it on the serial monitor. I add this delay, it's better to add it. We're gonna see why. So I upload this code to the Arduino. So the code is uploaded. Let's now open the serial monitor. As you can see, the value given by the sensor for 0 amp is 512, which means it's in the center of 0 and 1024. Those are the minimum and maximum values. So for 0 AC, it gives us the 512, just like the other sensor, the ZMPT101B. Let's turn on our light bulb. As you can see, the multimeter gives us a value, the correct value, but here in the serial monitor we cannot see anything. Even if I change it or something, we cannot see the values, correct values. That's normal. This code is only to show the shape of the signal, and this is what I'm gonna do now. So for this code, it's better to use the serial plotter. So here we have our serial plotter, and as you can see, the values are fluctuating around 512 or 511. Now let's turn on our light bulb. The dimmer is on full cycle. As you can see, we are now getting a shape of our AC signal, a sine wave like shape. But the only problem, as you can see, is that I'm using a 30 amp version, which means that the scale is very big. So here it's better to use 5 amp version or 10 amps. It will be fluctuating around 512, but with a bigger amplification. It could reach maybe up to 700 or 800, but now it's only fluctuating by some values around 512. Let's turn down the dimmer all the way down. As you can see, the shape has changed. It kinda looks like the shape of a light dimmer, a current in a light dimmer. Okay, so now we saw the shape and we saw the interfacing of the module with the Arduino. Let's test our second code, which permits us to measure AC current of a sine wave signal. So here we have our second code. It permits us to measure a sine wave signal. It's not that perfect, but it's okay. You can improve it if you want. Here we define our number of samples we're gonna take. Here I choose 300. It's okay. Here I defined my module pin. Again, it's in A0. Here I have other variables that I'm gonna use, like the high peak and low peak, and amps from peak to peak, because I'm gonna use the peak to peak method to calculate the RMS. Here, to establish our serial connection, I'm gonna add a pin mode. I forgot it. Okay, so here I'm using this function read amps. So what this read amps do, we have a counter here. Then I define my high peak as 0 and my low peak as 1024, because as you know the Arduino ADC goes from 0 to 1024, so I consider my 0 is the high peak and low peak is the 1024. So here I have my loop for, and as you can see I have my counter. It goes from 0 up to the number of samples we defined. Here we have 300, and it keeps increasing. So we read the value from the signal from the module, and we compare it to the high peak and low peak. If this value is higher than the high peak, so we change the high peak from 0 to the value found. And same thing, so first, like, we begin as our high peak is 0, in the last we're gonna find around 500 or 600 or 700. Then our low peak start from 1024 at the beginning, in the last we're gonna find it's around 400 or 300 depending on the module. As I said, the module can measure up to 30 amps. I'm working only with some few amps, not even 1 amp, so the values will goes only like high peak as 520 maybe, and low peak 500 or something. So here I do a little calculation, high peak minus the low peak. Then normally I should only convert it to amps by the multiplying times 0.3536. This is the formula to go from peak to peak to amps. But here, as I'm needing a further calibration, I am multiplying again by 0.06 just to get the correct values. So here, as you can see, my setup is still the same. Everything is still the same. I'm going to open the serial monitor. So on the left are the measured amps. As you can see, it's a little bit fluctuating. Normally it should be 0, but also on the multimeter is 0 and fluctuating a little bit around 0.01 or 0.02, sorry. Now I'm going to turn on my dimmer. As you can see here on the serial monitor, it's around 0.32 amps, and it's okay comparing to the multimeter. The values on the right are peak to peak values. Don't consider them. I just add them to make the calibrating right. So as you can see, this works well for sine wave signal. Now I'm gonna dim the light because I want that weird shape from the triac. I'm going to turn it all the way down. And here you can see the problem with this code. The multimeter, as you can read here, can measure the true RMS, which means now the true RMS of the signal is 0.21 amps. But here in the code we use it still reads the 0.3234 amps, which means it still reads from peak to peak, but the true RMS value is not that. This is the only problem with that code. So if you're working with only sine wave signal, we can use that code. It's easy to understand. Now let's pass to the third code, which permits us to read the true RMS. So here we have our third code. It will permit us to read the true RMS of any signal shape, not only the sine wave. And here I'm using this filters library. It will make the work very easy for us. Here I define my pin in A0 as usual. Here the ACS value, I get the raw value from the sensor. Here test frequency, I'm using 50 Hz. If you are working with 60, you can place it here. Here the window length for sampling purpose. And here for the intercept and slope, I'm going to go back to them later, because a lot of people have trouble with those. Here is where I store my last value, the amps through RMS, and here we have our sampling period. It's 1 second, so every 1 second we do the calculation, and here we define our entity input states. So here we define its length, and this input state is where we put our ACS value. So here I'm reading it from the analog pin. I store it in this ACS value, then I input this value on the input states input, and every second, so here every second I'm calculating actually this sigma, the signal sigma. So here, if you want to learn a lot about this how this library works, you can check its file, the CPP file of running statistics, and you'll find everything used, like the average signal, how it's calculated, and the sigma. So those things are related to the statistics and probability. You probably have studied them in school. And why are we doing all this work? It's because the calculation of a RMS or true RMS, it's very difficult, especially for electronics, because you should go from analog to digital signal, and you should do the sampling and calculation. And as you know, the RMS is calculated by using the integral calculus. It's pretty much tricky to put it on a board, on an electronic board, but we're glad that we have that library that do all the things for us. So the code is uploaded. Let's open the serial monitor. Let it get stable. It's not correct value. Okay, so here I have two values. I have without calibration, and amps. Amps is where I calculate my calibrated values. So here for without calibration, I'm not using intercept or slope, because the last time I used those values in the ZMPT101B tutorial, a lot of people kept asking me how I got these values. I thought it was simple and easy, so now I'm not using them, because as you can see in the code, I have input stat sigma. So now I have just that sigma. That's just, I'm gonna explain it, that's a true RMS value. Actually, this is a true RMS value. This one is true RMS value too, but this one is not calibrated. This one is calibrated. So I close my serial monitor just to see how to get this intercept and slope value. So here I'm going to add another thing to display. I'm going to upload it to the Arduino. Okay, open serial monitor again. Let it stable a little bit. So here, as you can see, I have three values now without calibration and the correct value. Then here we have thing that we're gonna test. As you can see, without calibration and test are the same. So first thing we check is the intercept. So because our intercept is 0, so there is no like an offset. Here we have 0 and 0, and also in the multimeter is 0, so there is no offset, so the intercept will be equal to 0. And this is exactly what we have here. If we had like a value we should remove it or add it to make it 0. This is how you get the intercept. And don't mind those values, those are just some fluctuations. As I said, the bigger scale of the module affect this. Actually it's 0. As I said, if we had an offset, you correct it here to make it 0. So here I'm gonna use it plus 0.
That doesn't make sense.
I'm gonna re-upload again, no problem. Okay, now we open our serial monitor again. We should have zeros everything here, as you can see, besides some little fluctuations. It's okay. Now we're gonna turn on our light dimmer. Let it stable a little bit. This is our reference, and we also have some calculated values. Like as I said, I'm using 75 watt light bulb and 220 volt or 230 volt AC voltage. Okay, so now as you can see here, I have 0.31 or 32 amps. Here in the correct values I have the same thing, 0.3231, which means the calibration is right. But here in our test we have 4 amps. We know that it's not 4 amps. It requires just a little calculation. So to get the slope value, all you have to do is to divide the correct value by the value you got. So here the correct value is 0.32. We divide it by 4.3, for example. And here, as you can see, our slope is 0.0744. Here the slope I found yesterday, it's 0.0752. This is how you get the slope, and you place it over there. We're gonna do it right now. This is the value we found, as I said. I'm gonna multiply it by this sigma. I'm gonna re-upload the code again. Open the serial monitor. Let it stable a little bit. And as you can see, now we calibrated our test to this value, and it has the same value as the calibration I did yesterday and the same as the multimeter. And now let's change the shape of the signal and see if our code works well. As you can see, it's 0.21 amps, and it's same thing showing on the serial monitor. But the last time we used that other code, it doesn't work with this weird shape signal, but this one works well. And it's faster than the multimeter. So unfortunately I end up breaking my old OLED screen. Rest in peace. So backup plan, I used LCD, but I still have the code for the OLED. I'm gonna add it for you to use it if you want. So I'm using OLED, I'm using the LCD. I have the code for it here. The code is very simple. We use that many times, just library and define the pins. I'm using the I2C version. And here, instead of showing the values on the serial monitor, you show them on the LCD. It's very simple and easy. Now we're gonna turn on our socket, then our light dimmer. It works well, and it's faster than the multimeter. So that's it for this module. I hope you like it. If you have any question, you can contact me, and don't forget to check the tutorial on how to measure the AC voltage. You can use them both, combine them both for a project to measure the power, for example. So that's it. Leave a like and subscribe if you want, and see you next time.